Welcome to Amazon Web Services webcast, Getting Started with Amazon EMR. Before we begin, I'd like to walk the audience through a few items. On your screen, you can see a Q&A pod. Please submit your questions at any time during this webcast, and our Q&A moderator will address them throughout the presentation. I will also answer a few in the live Q&A session at the end of this presentation. Today's webcast is being recorded, and we'll send you a follow-up email with the URL to the recording, as well as a link to the presentation deck. Also, my name is John. I'm a senior product manager with Amazon EMR, and thanks for coming to the webcast. Let's get started. So I'll run you through a quick agenda. We're going to go over a lot of different things about Amazon EMR at a high level, and then afterwards, happy to answer some questions as time permits. First, we're going to start out talking a little bit about Hadoop and some of the big data use cases you guys might have to frame the conversation. Then we're going to go through Amazon EMR 101. I'll run you through some of the feature set that we have and things related to that. We'll dive a little bit deeper into integration with AWS storage and database services that Amazon EMR has. And then we'll finish with some common EMR design patterns that will match up with some of the use cases that we start out with in the beginning, and then we'll answer some questions. So, data has become a commodity these days, and when leveraging large data sets and getting insights out of them, you run into a lot of architecture problems and problems with the tools that you use to get those insights. First of all, a lot of data, especially in this day and age, lacks the formal structure that you say you'd use a relational database to warehouse. Also, data is coming in at a variety of different rates. A lot of data is coming in, say, in streams. How do you process a stream and get real-time insights out of information coming in? Data sets are also getting a lot larger. There's a lot more information out there, and almost everybody's mobile device, and there's a lot of metering things amount to a very, very, very large data sets that are, with the traditional tools, are hard to warehouse and query. You need to be flexible for undefined and ad hoc analysis. A lot of times, you don't necessarily know the types of questions that you want to ask when you're building your architecture, and you need to be able to be agile in using new tools and accessing new types of data to dive deep and figure out the types of answers that you're looking for. Finally, speed is also important. You scale out your data and you have a lot more data that you want to query, but if the result came back 100 times slower, it still wouldn't be useful. A lot of times, actionable insights and the speed to those insights is incredibly important. So the speed of queries on large data sets is also a problem that traditional tools can't typically handle. So the Hadoop ecosystem, which has been around for around a decade, actually, probably a little bit less than that, has turned into one of the more popular tools to handle big data problems. And there's really several reasons why Hadoop has become adopted for these types of things. First is it's massively parallel. So traditional systems might be on one large node and be limited by the compute and memory capacity on that one node. Hadoop is massively parallel, and the Hadoop system spins up many different nodes and breaks up one job and processes each component in parallel. It's also scalable and fault tolerant. Because it's a parallel system, some of the processing and storage components in Hadoop can withstand failures of any one given node and rerun that job or have the data distributed on other nodes so that there won't be a failure in the system or in the job that you're trying to process. It's also scalable, as once again, it's a distributed system. You can add on more compute, memory, or storage capacity into the system to handle larger and larger workloads. It's a flexible platform. There are many different languages you can query using SQL, Scala, write programs in Python. Its history is in Java. So really any type of developer expertise that you have can use this system and immediately start working with it. Hadoop is open source, which is very important because of the rate of development among all of the ecosystems. And we'll go through in a little bit all of the different applications that live in the Hadoop ecosystem and some of the, or at least a subset of them, and what you can use them for. But because they're open source, there are tons of contributors all around the world working on building new features and fixing bugs in all of these projects, And the speed of evolution of each of these projects is incredibly quick. And a lot of projects that have only been around for a couple of years are starting to become incredibly popular just because of the velocity of these projects. There's an ecosystem of tools around Hadoop as well. So there's many BI tools, visualization tools, tools to help you orchestrate workflows. Because Hadoop's been around for a while, and we'll go through a little bit of that later, there's a lot of other tools and third-party tools you can use with your system. And finally, it's, batch and real-time analytics is flexible. There's many different types of use cases that you can have, and there's typically a tool in the Hadoop ecosystem that'll match with that use case. The history of Hadoop started with Hadoop 1, which is really meant as a workflow engine. As you can see here, you have a storage layer, and then the engine is for batch processing, MapReduce. And MapReduce at a high level takes a problem, distributes amongst all the Hadoop nodes, and then does processing locally on each node, and then reduces it back into the end result of the job. And it was primarily used to just process large data sets. Over the last couple of years, I think about the end of 2013, Hadoop 2 was launched, which turned Hadoop more from a batch workflow engine into a clustered application manager with the advent of Yarn. So Hadoop 2 clusters not only did batch MapReduce jobs, but also have other engines that can do more interactive queries, a lot of times leveraging a lot of memory. Applications for that, and we'll go through some of these later, plug in on top of these different engines to allow you to do batch processing, machine learning type jobs, and many other things as well. There's also in Hadoop 2, or I guess Hadoop 1 also had some of this, but other applications that live in the ecosystem, like HBase, which is a NoSQL database, Presto, which is also just a different type of engine, and Impala with another engine, and both of those are used for ad hoc SQL queries. We've seen a lot of customers across many verticals adopt Hadoop because it's so flexible for a variety of different data processing and warehousing use cases. And here's a subset of some of EMR's customers. A lot of these have case studies either on our big data blog or on our website. But as you can see, many different verticals from many different use cases have adopted this, ranging from Yelp and recommendation engines to Netflix to ad technology companies like Adroll, financial regulators like FINRA, gaming companies like Rovio. In all these verticals, there are big data problems, and we've seen EMR and Hadoop become adopted by these companies to solve those issues. So that's a little bit of background on Hadoop at a very, very high level. And we'll get into EMR. So EMR has been around since 2009, back when Hadoop 1 was the main platform before Hadoop 2. And it was built really because managing Hadoop clusters and setting them up is not easy to do. And we found that customers really want to spend more time accessing the data and deriving insights and value from it than spending a lot of time managing and setting up their Hadoop clusters and upgrading them and those sorts of operations. So we built Amazon EMR to make it really, really easy, performant, and cost-effective and secure to run Hadoop in AWS. And there's a variety of reasons that really boil down to these, I think, 6 main points about why we see customers choosing to run their Hadoop jobs in EMR. It's easy to use. It's low cost. You pay an hourly rate for your cluster. You're not locked in by having to choose your cluster, the hardware and all of that, and then have it forever. You can use what you need. And that goes right into the elastic nature of EMR. Reliable. We have a lot of monitoring tools and also some cluster management automatic tools as well. Secure and also flexible. And that's where all these applications come back and really allow you to customize what you're running on your cluster. So first, we can quickly go through some of these points. Ease of use. So it's really easy to deploy a Hadoop cluster. Instead of an EC2, you spin up a bunch of nodes and install Hadoop and configure it, make sure that it's working, and then start actually doing some processing work with Hadoop. In EMR, you can deploy a Hadoop cluster with up to several thousand nodes, literally in a couple of clicks. And actually, I'll show you later a quick run through of our console that'll, so all these points that I'm bringing up will come together when you can see it in the console. But in the AWS Management Console, you click on EMR, you click on Create Cluster, you can configure a few things or not, hit Create Cluster, and you're there. An EMR control plane will go in, spin up all the nodes, install everything, make sure everything is managed and working, and then execute your job or allow you to tell it what to do next. We also integrate with the AWS CLI. There's a set of EMR commands on there. Same thing, AWS EMR Create Cluster. You can put in a few parameters. We have a lot of sensible defaults, so we make it so you really only have to specify a couple of things. Hit go, or enter, I guess, and you're off. The cluster gets created, and within a couple of minutes, you have a fully functioning Hadoop cluster with the applications you want, ready to actually do some work. Finally, EMR is an API-driven service, and you can use an SDK and create your own programs to call the EMR API to create clusters and manage your workloads as well and submit work. And we have many customers using all three of these ways. Typically, once you get into production, you'll use the API and just script against the command line. And the console is great just to kick the tires and do a lot of testing. One other thing is when you're creating your cluster, it's important to choose the right hardware to get the right performance for the job. Typically, as I mentioned before a couple slides back, Hadoop workloads really vary in the hardware profiles they need. Whether you're running, say, a machine learning job, an interactive ad hoc query job, or just a batch reporting process that needs to finish in a certain amount of time. Each of these might need different compute resources, different memory resources. Or if you're running a large HDFS cluster, you'll need instances with a lot of disk. So EMR makes it very easy to just, when you're creating your cluster, select the instance that you want. And you could even make it job specific because it's easy to create a cluster. You can create a cluster for a specific Hadoop job, take it down when it's done, and then spin up a new cluster with a different instance type for the different job. And here's some examples of the instances we support. M3 for general compute, C3s for more intensive compute jobs, R3s for large memory jobs need a lot of memory, and if you're running large HDFS clusters, the newly launched D2 instance is supported. So EMR takes advantage of EC2. EMR spins up clusters of EC2 instances, so you truly get elastic capacity and you pay by the hour, which is important when you're running a variety of different Hadoop jobs. We also integrate with the EC2 Spot market. So this slide demonstrates what we see a common use case of how to mix the different instance markets to be able to get the lowest cost for your job. So an on-demand EC2 instance, you pay per hour for that instance type, and then you shut it down when you're not using it anymore. EC2 Spot capacity is slightly different. You bid on the instances you want, so you choose the price, and there's a market price for that instance that's dynamic in the spot market. And if you bid above that price, you get that instance for as long as the market price is under your bid price. So a lot of times we see that you can save up to 90% off the on-demand price by bidding. However, the problem is that if the market price goes above the bid price, you lose the node. Hadoop, though, is a fault-tolerant system. So if you lose any one node in your cluster, except the one running the master node, which you would never want to run on Spot, your job will still continue on. So we see customers running a mix of on-demand and Spot instances to get a low cost, but get the job done in a certain amount of time. You would use your on-demand for nodes that you don't want to lose, saying, this job needs to get done in this time. I need this many nodes to complete it, and I don't want any chance of them getting taken away. However, you can also add on, and the next slide will demonstrate this a little bit better, other groups of instances with Spot capacity to say, well, if I can get this capacity for this price, I'll take it and complete my job more quickly. But if I can't get it, I lose those nodes while my cluster is running, that's okay because I still have an on-demand group. And EMR really lets you tailor the number of instances, the type of instances you want, and whether the group is Spot or not. And I can quickly walk through this diagram of EMR instance groups that create up a cluster topology. So EMR clusters have one master node, which runs name node for HDFS, resource manager for Yarn. It's the gateway that you'll connect to if you want to submit jobs to the Hadoop API, and it runs some other important processes as well. Then you can add nodes to the cluster in the different slave groups, and there are two slave groups in an EMR cluster: core and task. The difference is that the core nodes run data node, and they're taking part in HDFS, Hadoop distributed storage, and slave groups do not run data node, but they do take part in Yarn and run Hadoop tasks. The reason for this is that when you're sizing clusters up and down, you don't typically want to size HDFS down because you could run out of space if you take away too many nodes. But because task nodes aren't running data node, they're not taking part in HDFS, you truly have capability to scale those up and down however you like, because you don't really have risk of data loss. And those also make it perfect for Spot nodes, because if you lose a Spot node, you're not disrupting HDFS, and Hadoop will rerun the task running on that node on a different one. So we see this cluster topology very often. You run on-demand nodes for your slave group core, and then for your slave group tasks, you can bid on capacity in an opportunistic way to complete your jobs faster at a lower price. I already brought this up a little bit. Easy to add and remove compute nodes. You can do that from the console or command line or API. And when you add a new node onto your cluster, EMR will take care of installing all of the necessary components onto that node and then bringing it into the cluster. Same thing when you remove a node as well. So you can really match your compute needs with the actual number of tasks that you're running on that cluster. Also, another way that EMR is really elastic is storing your decoupling your compute and storage by storing your data in Amazon and S3, and then having dynamic EMR clusters whenever you need to process it. It saves a lot of money because you don't need your cluster on all the time. Instead of storing data in HDFS and requiring all of those nodes, if you were doing that, you couldn't shut down the cluster and still keep the data in HDFS. Pushing it down into S3, and we'll go into this a lot more detail later, allows you to only need the cluster up when it's doing work. So this obviously saves a lot of money because when the cluster is not running, you're not paying for it, but you also keep your data in a very durable, elastic, and low-cost AWS storage service as well. We have a variety of monitoring options. EMR service does do some monitoring on its own and replaces poorly performing nodes under the hood, so you don't have to worry about some of those management tasks. However, we'd still recommend it's good to monitor how your jobs are doing. If your job is an error, obviously you'll have to debug it. And we built some tooling to make that a little bit easier. In our console, we have CloudWatch metrics. I think we have 23 different metrics. You can also define some of your own. They keep track of cluster node, IO specific things, MapReduce specific metrics. So you can quickly tab through and see, how's my job doing? Is there a bottleneck anywhere? Should I add more capacity? And answer those types of questions. You can also install Ganglia on your cluster and access it on the master node by SSHing in and accessing that UI. And that has even more metrics that you can look at, or the Hadoop metrics are also available in that fashion as well. We also have debug tools that help organize your logs so you can quickly go through them and troubleshoot it when one of your jobs might fail. Finally, EMR, you can select logging to S3, and the EMR cluster will actually push all of the logs from the Hadoop cluster into the path that you specify into S3, which makes it great if you're running transient Hadoop jobs. The example I gave you before, where you have data in S3, you spin up an EMR cluster, process the data, and then shut the cluster down. Your logs, if they were on the cluster, you wouldn't be able to access them to see what happens. But by enabling this, EMR will push your logs during the job to S3. When it shuts down, push the final logs to S3, and then you can go look at your logs while your cluster isn't there. We have several security features that I'd like to highlight with EMR. We first integrate with IAM roles, and this is important just in locking down the permissions that your cluster has in AWS, and we see this as a very popular feature with customers. The IAM roles give AWS services fine-grained control over delegating permissions to other AWS services and access to AWS resources. EMR, the EMR cluster, if you're processing data in S3, you need to give it permission to actually be able to call the S3 APIs, go get the data, and then re-put it back. And EMR, the service, needs permission to manage your instances. We want to make that as transparent and customizable as possible. So through applying roles to your cluster, you can use the default ones, which have all of the default permissions that EMR needs to run. But if there are certain things that you want to tweak off or certain features in EMR that you know you're not using and you don't want to give it permission to, say, call DynamoDB, you can turn those off and customize the permissions that EMR has. EMR launches clusters in security groups. Once again, we have a default option, which most customers use, but if you have custom needs for, actually, first explain it. Security group is a virtual firewall which controls access to the EC2 instances that make up your EMR cluster. And we have two groups, a master security group and a slave security group. Each have different permissions. One of the big differences is the master security group serves as the gateway node, so it allows you SSH access, while you cannot SSH directly into the slave security group. That's more locked down on purpose. So we provide a lot of these by default to make sure your cluster is secure. However, if you have different security needs, you can add on more security groups that more tailor the egress and ingress permissions on your cluster. A few other security features that I'd like to highlight. EMR FS, which we'll talk about a little bit more, that's our file system for S3 that allows Hadoop to process data performantly in S3, integrates with several S3 encryption features. S3 server-side encryption and S3 client-side encryption. We'll go through a little more of those in more detail later. EMR integrates with CloudTrail, so you can track who's calling your Amazon, your EMR APIs, and what those calls are. And finally, you can launch your Amazon EMR cluster in a VPC, which is a largely isolated portion of the AWS network. Besides some great security features, it also enables enhanced networking on certain new instance types for better performance. Finally, the last point, EMR truly is a flexible cluster management system, and we really give you control to install whatever you'd like to run in the Hadoop ecosystem on your cluster. We have several applications that we have natively available, and also I'll go through quickly Bootstrap Actions, which allow you to really install whatever you want. So first, and I'll give a little bit of details on what these are. Actually, we can go back. Currently, we support Hadoop MapReduce, Pig, and Hive, which are higher level abstractions over Hadoop MapReduce, and we'll go through that in a minute. Impala, which is a fast SQL query tool, HBase, which is a NoSQL database, and Hue, which is a UI for some of these applications. So Hive is one of our most popular applications that you can install on your EMR cluster, and it basically is a SQL overlay over Hadoop MapReduce. So instead of needing to write a Java MapReduce program, you can write your workflows in SQL, and Hive will translate that into MapReduce on the cluster, and then Hadoop will go execute the job. Hive's a really versatile tool. You can use it for batch reporting workloads or ad hoc workloads. If you have some questions you want to ask of your data and know how to write SQL, you can write it and submit those jobs to Hive. You can query data in HDFS and S3, and it uses schema on read, which is great because if you have a data set, you can define the schema and how you want Hive to look at that data set before executing the query. So instead of needing to load data into a static relational format, you really can choose how you're interacting with your data at runtime. Finally, there are other engines that Hive is beginning to integrate with. One popular one is Tez, which is an alternative to MapReduce. And I won't go into details of that here, but there are options to use that engine for faster ad hoc queries. Pig is similar to Hive in that it makes it makes that you don't have to know how to write a Java MapReduce program to be able to use Hadoop to do work. Instead of SQL, though, it uses its own language called Pig Latin, which is really great at deriving data flows. Pig is commonly used more for large ETL workloads. It also has many great built-in many built-in functions. Also allows you to create your own user-defined functions as well. So it really is a powerful ETL tool when you have raw data being put into S3 and you want to transform it either for reporting purposes or for loading it into, say, a more traditional data warehouse. HBase is another tool that you can launch on EMR, and it's the NoSQL database in the Hadoop ecosystem. Incredibly scalable, billions of rows, you can have millions of columns. We've built some features where you can back up and restore your tables to S3 as well. So we see people using HBase for many different use cases. And it's a great alternative to Cassandra or Mongo and some of the other NoSQL tools. Impala is primarily used as a data warehouse for Hadoop. Currently, it does not integrate with EMRFS, so if you're using Impala, you need to store your data on the cluster in HDFS, but it's an incredibly fast, low latency SQL query engine, and we see a lot of customer success in people running Impala clusters to do ad hoc interactive queries, and you can run it on structured or unstructured data, or even on top of an HBase table as well. Also, many BI tools integrate natively with Impala, like Tableau, and you can spin up a Tableau instance and connect it to Impala running on EMR to be able to visualize your results using that tool, for instance. Finally, and I'll show this to you in a minute because I have a cluster with Hue up and running, but Hue is available in EMR as an easy way to access Hive and Pig. So instead of submitting your jobs through EMR Step or doing it directly on the command line, Hue has a Hive editor, which allows you to, almost like a SQL developer interface, write your queries. You can browse tables, save queries, and you can have many people logged into one Hue instance querying the same cluster. Here's a quick screen of the job browser. We'll go through that in a minute. So we have several applications that you can launch natively, and literally it's as easy as just clicking on it in the console or specifying it from the command line to trigger EMR to install. But the Hadoop ecosystem is moving fast. There are many different new tools coming out, and you have, using Bootstrap Actions, the ability to install any of these. These are just a few examples, but anything on your cluster. A Bootstrap action is a script that you provide the cluster that runs on every node at cluster startup before we start Hadoop on the cluster. So you could write a script to install, say, Presto on your cluster, tell the EMR create cluster command, use this script as a bootstrap, and when the cluster is being created, we'll do whatever you told it to. In this case, it'll install Presto. You have root access over all the EC2 nodes in an EMR cluster than your account, so you really can do whatever you'd like with them when you're installing things at startup. We have a variety of Bootstrap actions on our GitHub that you can play around with. It's at Presto, Phoenix are there. We also have a Bootstrap action for Spark, which we've seen very popular. Right now, I think it's installing Spark 1.3.1. And we see a lot of interest around Spark. I personally am a big fan of the tool. It's an alternative to Hadoop MapReduce. It's an alternative engine, and it has its own ecosystem of applications as well. It doesn't use the MapReduce framework, and it's subsequently faster than Hadoop MapReduce at processing certain types of jobs It's great for iterative machine learning queries, and actually Spark comes with MLlib, which is a set of libraries that you can begin using right off the bat without having to write your own machine learning libraries. It comes with a SQL interface, same thing as Hive to Hadoop. Spark SQL for Spark translates SQL that you write into Spark jobs. And finally, it comes with a tool, Spark Streaming, which allows you to do stream processing. And we'll get to an example of that a little bit later. Bootstrap Actions are also very useful besides installing applications and configuring them as well. We have sensible defaults for all the Hadoop applications you can install, but a lot of times after you're running a job, you start seeing the resourcing patterns of that job, and you can start making configuration tweaks to really get the best performance out of your system. So it's easy to configure. You use this Bootstrap action, configure Hadoop, specify the configuration file you'd like to overwrite the values on, and then supply the configurations that you want to change to that Bootstrap action. And when the cluster starts up, it'll overwrite those values in those configuration files, and that'll be the new configuration for your cluster. So very easy to do, and it's quick if you want to do testing to validate some of these performance changes. You can fire up many different EMR jobs with different configurations to quickly test what makes the most sense. Submitting work to any of these applications on the cluster is pretty easy. There's two ways that we see customers do it. First, EMR has a Step API high. You can call the step performance benefit from using consistent view. Also, just one more thing is you can configure all that from the console, and you do have to manage the EMR/FS metadata outside of the cluster. So even though EMR is updating the metadata when new information is in the consistent view lens, you'll have to terminate the metadata when you want to get rid of the consistent view. We don't have much time, so I'm not going to explain this in detail, but we recently launched a feature that allows EMR/FS to transparently support objects that were uploaded to S3 with client-side encryption using either a key you provided from anywhere or the newly launched Amazon AWS key management service as well. And it integrates tightly with both of those methods of supplying keys to objects. If you've encrypted objects to S3 using those keys, all you have to do is either specify the KMS key that you'd like to use to encrypt objects to your EMR cluster, or supply a custom encryption materials provider which has the logic to access the keys that you needed to access, and EMR will, under the hood, encrypt and decrypt the objects so it can process those in a performant way. EMR also integrates with Amazon Kinesis. You can use Hive, Pig, and Hadoop from an EMR cluster to read from Kinesis streams and do processing. And this really bridges the Hadoop batch world with Kinesis, which is a streaming ingest service in AWS. We see many customers having success with this architecture. EMR using Hive can query DynamoDB, so you can get a SQL query interface for DynamoDB, which is a NoSQL database service in AWS. We see customers doing a variety of things with it. You can use it to load data from S3 into Dynamo. You can back up Dynamo to S3. You can run an EMR query and join data living in Dynamo with whatever your EMR job is reading from other data sources as well. So it's a good hook into having more accessibility into your data that you're storing in Dynamo. Finally, one last way EMR integrates with other AWS data services is with Redshift via data pipeline. One very common use case is to use EMR as an extract, transform, load tool to take data out of S3, unstructured data that you've pushed in, transform it into, or do aggregations, that sort of stuff, push it back to S3, and then load it into Redshift. And AWS Data Pipeline is a orchestration scheduling service in Amazon that can orchestrate this whole flow that I'm showing you here, and run it on a scheduled interval or in response to other indications as well. So a lot of information, and if you have any questions, please send them over and we can respond to them as we can. I'm going to quickly run through some design patterns. We don't have much time left, so I'll go as fast as I can. So one example which hammering home the use of EMR and S3 is just a simple batch processing example. Gigabytes of logs are being pushed to S3. In this example, that actually is what Yelp does, and they have a case study here about it. Data gets pushed to S3, and you want to run a reporting job. You spin up a daily EMR cluster running Hive, and you have a bunch of Hive scripts to run. EMR will process that data using those scripts, output the results in the reporting, and then shut down at the end. And you have your output set in S3, those reports ready for consumption. And because EMR is incredibly scalable, it can handle 30 terabytes a day, or if you have different amounts of data each day, you can customize your cluster size to make sure that you're not over provisioning compute capacity in your cluster to do the job. Another general reference, same idea, data is being pushed to S3. You have transient EMR clusters for daily batch jobs, and a long-running cluster also running Hive that analysts can submit work to do ad hoc investigations with data, either in this case in HDFS, the data could be in S3 or both. It's very many options for the data layers for your EMR clusters. Here's an example from Clashlytics, which was recently acquired by Twitter. They actually presented this use case at our SF Summit. Same idea in this case, using many different EMR clusters running different applications that are job specific against data in S3. In this case, the flow is data gets pushed into an Amazon S3 bucket, S3 distributed copy, S3 disk CP, which is using EMR under the hood, is taking that raw data, putting it into LZO format, and probably doing some other small transformations and maybe putting a lot of small files into larger files just for better performance with EMR into an intermediate bucket, and then spinning up several different EMR clusters running different applications for specific data processing purposes, and then outputting the final result set into S3 and then shutting down all the compute resources so you don't have to pay for them anymore. So a second example is using EMR instead of as a workflow engine, using it more as a long-running cluster for a database application. In this case, a common thing we see is, once again, S3 is your starting point for data typically. Data is pushed to S3, and there's a daily pig job that runs that does ETL, transforming the data and aggregating it and then loading it into an EMR cluster running Apache HBase, which is the NoSQL database for Hadoop, which is great for a lot of concurrent reads and fast responses. So a lot of times we see HBase tables backing a front end, a UI, to be able to serve up information very, very quickly. And that is running an EMR. EMR is managing that cluster. Ad hoc query over S3 is another very common use case. This also highlights the use of Bootstrap Actions. So Netflix wrote in their blog about a way they use EMR where they have a petabyte data warehouse, a lot of data in S3, and they create EMR clusters when their data scientists want to do some ad hoc analysis using Presto, which is a tool that we don't officially support, but we have a Bootstrap action that easily installs it on an EMR cluster, and you can read data from S3 directly and do very, very, very fast SQL queries, and it has an ANSI SQL support. Another example is using EMR as both a ad hoc query tool over large data sets when you need to do queries over data set that size, like a needle in the haystack problem, but also using EMR as an ETL tool to load data into a traditional data warehouse that has maybe a subset of that data or aggregates, but you use for daily reporting or other BI use cases. In this case, we saw a customer using Spark and installing it via a Bootstrap action to both do an hourly EMR job to load fresh data into Redshift for regular reporting and well-known queries, but also using Spark, probably a couple times a week to really dive into the raw data to find weird anomalies and things of that sort that you wouldn't have been able to find in the aggregates that were loaded into Redshift. So once again, EMR, very versatile tool, can use batch processing, but also for deep ad hoc analysis. And finally, you can use EMR with streaming data as well. This is a typical streaming data flow and common sets of tools for each part in the pipeline, from where sensors emitting log data to continuous processing on that stream to being loaded into a data warehouse for analytics and reporting. So you can see a lot of different tools you can use, and it can get very complex. We found that through using Amazon Kinesis and Amazon EMR, you can really simplify this data flow by using Amazon Kinesis as your streaming data repository, ingesting data in those streams, and then using EMR either with more batch type processes like Hive, Pig, and cascading on top of Hadoop to run maybe not necessarily stream processing, but micro batch processing, or using Apache Spark streaming to do more real-time, very near real-time processing on that stream, all of which can run in EMR and get data pushed from Kinesis into those applications. It looks like my thank you disappeared. But thanks a lot, everybody, for listening. A lot of information. Hopefully,